Well, I'd like to start, as always, with the beginning, and the beginning is the etiology. And it's not that the etiology has changed much since yesterday, when I presented it here, but I think that it's important to put the technology of friction reduction, and specifically the parafricta technology, in the context of the etiology. And so, why is it important to reduce friction at the interface between the body and the support in order to protect tissues? And I'm saying tissues deliberately, not the skin, but tissues, because tissue protection spans from protecting the skin to protecting the deepest tissues, those that are in the vicinity of the bones. And what I'd like to focus on today is the effect of reducing friction on protecting tissues across that spectrum, from skin to the deepest. As I was saying, we are constantly and continuously deforming the basic living structures in our body, which is our cells. And as we apply our body weight, and it doesn't matter if it's during sitting or during lying in bed, we distort the tissues. And we distort the tissues in a complex manner. We compress them, but we also stretch them, and we also shear them. And within these tissues, there are cells, and the mechanical loads are transferred across the multi-scales, the multi-dimensions, from the macro to the micro, from the tissues to the cells. And cells are distorted, and cell structures are distorted. And when you look at an individual cell, it's quite a complex structure by itself. It's mechanically designed, you could say, to support loads, but of course, like any other structure, like any engineering structure, to a certain extent. And if you exceed that tolerance, you may damage the structure of the cell, its scaffold or skeleton, its walls or envelope, much like if you would overload a bridge or an engine, you would cause damage to that structure. And as I was mentioning, over nearly 20 years of a career path, I've been looking at different model systems to understand what is it about deformation that originates from body weight that damages tissues. And as was very nicely phrased in the previous session, the first thing that you need to do is to measure those deformations so that you can do something about them. And a direct approach for measuring deformations in the living human body is to use the wonderful imaging technologies that we now have, primarily MRI. So you can actually demonstrate, visualize, quantify tissue distortions in MRI settings, especially in weight-bearing MRI trials, like what you can do with a seated MRI configuration to which we had access. And then you can actually measure these distortions of deep tissues and then ask the question, okay, in a different living model system, of course, you can't ask the question how much time it will take until I produce damage in that individual here. But in a different model system, for example, an animal model, you can then recreate those loads and look at tissue viability, again at the macroscopic scale and the microscopic scale, and in even more, I would say, modern research tools, such as what tissue engineering can offer us, you can basically build, like in a Lego system, a model of a tissue to which you can apply loads, controlled loads, at controlled conditions, thermodynamic, biochemical conditions, and look again at the viability of the tissue at the scale of individual cells. Or you can look at the individual cells isolated from the tissues and deform them directly using different model systems that we have developed for that. And all of that together indicates that even if you don't account for perfusion, so regardless of the ischemic conditions, deformation and distortion by itself can damage cells, much like in the examples that I've mentioned of machinery parts or bridges. Cells are structures, and structures can be damaged by deformation. And going back to this example, which I think illustrates it very well, that if you deform a living body enough, you will eventually break their skeleton. And, you know, this is old knowledge, right? It goes back to that, in the sense that if you deform a cell for long enough, without giving the person the ability to respond to that load, because, for example, of neuromuscular impairment, or because he's under anesthetics, and the load just continues and the deformation is sustained, eventually you'll break down the skeleton of the cell and the other structures of the cell will follow and fail. And that will interfere with the cell's ability to control phenomena such as transport, homeostasis, and will eventually lead to either necrotic or apoptotic deaths, depending on the magnitudes of loads. So we start the discussion by stating that deformation is the primary cell killer. And it can kill cells directly by damaging the structure, or it can kill cells indirectly by affecting the vasculature and the lymphatics. But it's the deformation, really. So you need to mitigate the deformation. And, of course, we can't forget about perfusion. Perfusion is important, but if you look at a time scale, impaired perfusion would affect cell viability in a scale of hours. And deformation, on the other hand, can inflict damage within tens of minutes. You can see that in different surgical procedures. You can see that on spinal boards. There are many examples from real-life scenarios that actually prove that. But now we also have the evidence from these laboratory studies that indicate that you need to minimize the deformation. Now, to the real world. Think about a patient who's lying in bed. His body weight pulls the body structures downwards because of gravity, especially if the head of the bed is elevated. So he's tending to slide in bed. And then there is frictional forces that are developing between the skin and whatever that skin touches. It can be the clothing, it can be the mattress, any support surface. And of course, it's not a movement on just one axis. There can be rotation, etc. So a lot of frictional forces which create shear in the tissue. That is distortion of parallel planes in the tissue structures once against each other. And again, that translates to the level of individual cells. And much like the macroscopic structure of the tissues and the vasculature, which are distorted in shear, the cells themselves are distorted in shear, and hence the cascade of damage to the cell skeleton and envelope the plasma membrane of the cell, and eventually the loss of homeostasis and viability. Basic physics elementary physics, actually high school physics, indicates that frictional forces are proportional to what we call the coefficient of friction, which is a physical characteristic of the two interfacing materials. If these are two rough materials with a rough topography or microtopography, they will create high friction, much like what happens with your car when the tires of the car are contacting the road. And if it's very smooth surfaces, then the coefficient of friction is very low, like what happens on, when there's ice contacting ice, so there is ice that is melting there, so there is a layer of water there, so it's very smooth, and hence the low value of the coefficient of friction, and the frictional forces will be proportional to that coefficient of friction. So what you want to do in order to minimize these exposure to deformations is to minimize the coefficient of friction, really. So how do you do that? First of all, you can offload, have no contact at all. That's ideal. And here is a study that we've published some years ago showing that if you have no contact, that's not a big surprise, I guess, to anyone. If you have no contact, there's no tissue distortion. You're looking at the cross-section through the foot, showing the heel bone. This is the calcaneus, the heel bone, and the fat pad, which is enveloping it. You can see the very irregular structure of the bone here, and the distortion in that soft tissue, in that fatty soft tissue, as you are creating contact with different surfaces, with the maximal distortion, of course, being generated when the heel just contacts a very rigid surface, like a table. And obviously, once there is physical contact, there is distortion, and that distortion will depend on the, as I was saying, the coefficient of friction. But in terms of practicality, if you try to avoid contact, and even if that individual is spontaneously moving, and or someone is basically moving him to take care of that patient, you may quickly find yourself in a position where the heel is supported by some surface that wasn't supposed to support it, where you wanted it to be suspended. So this is quite tricky. The other thing is that the individual anatomy is also a very dominant factor in determining these tissue distortions. So we don't have the same structure of noses, right? Our noses vary. Our heels also vary, and our heel bones also vary. Some of them are sharper, some of them are more blunt. So it depends on the vulnerability of the individual. There are also extrinsic factors. For example, if the temperature is high, could be the temperature of the environment, or it can be intrinsic if it's just a patient who is fevering, or if there is moisture and wetness in the environment, the surfaces will change their physical properties. The skin, for example, we all know that when we take a bath, right? The skin, for example, will become more wrinkled. So that's a change in topography. That will actually create more friction and elevate those frictional forces. And those frictional forces, whenever there is contact, are transmitted, are transferred from the contact surface internally into the body. And this is a computer simulation that, again, we've published a couple of years ago that demonstrates how these contact forces are transmitted internally into the body and create distortions in the adjacent soft tissues. And this is another paper showing specifically what happens internally in the structure of the soft tissues of the heel. So basically, we took off the heel bone here to just show what's going on at the interaction between the heel bone and the soft tissue, which is right here, the red colors, and red is not good. Red is bad, right? So all this red indicates very high tissue distortions that are generated by the forces that are transmitted over here at the surface. So shear deformations that correlate to frictional forces, which in turn correlate to the coefficient of friction, are transferred internally into the soft tissues to the site around the bone, to the bone-soft tissue interface, where they maximize, as you can see here. Hence, if you do something about that interaction, if you, by selecting the right materials, minimize that coefficient of friction, you can avoid that deep tissue distortion that may cause the deep tissue injury, which clinicians would describe as heel ulcers. And again, it's all about the topography of the materials. So if this is a standard fabric, and you can see the rough topography in microscopy, of course, this is a much smarter material with controlled topography properties that are designed to minimize friction. And by putting two of these layers together so that they slide against each other, they basically absorb the frictional forces, preventing most of them to be transferred inwards to the body. So I'll wrap up here by summarizing the major points in my talk. The damage originates from exposure to sustained deformations, which compromise cell viability and function. Hence, the objective should be to minimize exposure to deformations, not only at the skin, but also deep in the inner layers of the relevant tissues. The posterior heels, in a patient who's lying in bed, being such a place of interest to prioritize in protection. And one of the promising approaches is to use smart textiles, as was mentioned here before, particularly low friction fabrics that reduce these frictional effects. The bottom line is prevention is the way forward. And that's the message that me and others in this conference and in other venues are promoting. And managing friction is a key component in effective prevention. Thank you for listening, and I'll be happy to take one or two questions if we have time.